Well, good afternoon, and welcome to the last session of the day. My name is J.R. DeShazo. I'm director of the UCLA Luskin Center for Innovation and a faculty member here at UCLA. And it's my pleasure to welcome you to the session that really ought to be titled Biodiversity, Anglers and Farmers, you know, the effects of climate impacts. I want to start by recognizing our sponsors who have helped make today's event possible, Southern California Edison, Borough Happold, and the California Strategic Growth Council. We appreciate your support, and then the many partner organizations that have helped get the word out and support the event more broadly. I want to just remind the audience that if you need to, you can adjust your viewing interface, the screen that you have there. You can use the different buttons to minimize or maximize, to drag the various parts of your screen around to make it comfortable for your viewing. And it's my pleasure to introduce a really terrific panel, 4 very interesting sets of papers that you're going to get to enjoy this afternoon. I am going to kind of introduce them one at a time, and they will have about 16 to 18 minutes to present, and then we'll have approximately 5 to 7 minutes for Q&A. I encourage you to submit your questions through the Q&A chat box, which you should be able to see there at the bottom of your screen as a participant. And I'll select, they'll be able to see the Q&A. I'll select the questions to prioritize if there are numerous questions and if we can't get to all of them. Let's proceed and get right into the content of today's session. It's my great pleasure to introduce our first presenter, Fran Moore, assistant professor at the University of California, Davis. Her paper is going to talk about Noah's Ark and the rising seas, climate change, biodiversity, public adaptation, and costs in the United States today. And I have to say, I think she's working with a data set that started when I was a PhD student at Harvard back in 1996 or 97. So I'm delighted to see that that this data set started by Weitzman and Merrick has continued to serve researchers' needs. Fran, take it away.
Thank you so much, and thanks, JR, and thanks to kind of everyone putting on this awesome conference. I've really been enjoying myself all day listening to these great talks. And so, yes, today I'm going to be presenting this paper. It's a fairly new paper, so kind of definitely interested in feedback. And this is joint work with Ariana Stokes, who was a kind of student at Davis, Xiaoli Dong, who's an ecologist in my department, and Mark Conti, who's an environmental economist at Fordham. And the area we're thinking about here is the problem of climate change impacts on natural systems. So if you think about the effects on natural systems, those climate change impacts are large, they're direct, and they're irreversible. And these estimates of, and it's in some ways they're kind of they're one of the kind of principal kind of effects of climate change that we think, you know, that we understand and know about. And we're sorry, I have a dog situation. We're experiencing them kind of today. But the estimates of the cost of ecological climate damages, as certainly as captured in kind of some of the models used to estimate the social cost of carbon, are kind of definitely incomplete and certainly dated. If you think about the types of the set of effects of climate change, we can roughly divide them into 2 components. So the use values, and use values is kind of anything that contributes to consumption. So kind of through the provision, say, of ecosystem goods and services. And then non-use values. So here I'm thinking primarily of climate-driven changes in extinction risk. And this component of climate change damages that I'm going to be talking about today. So what are the so just to kind of set the scene in terms of what we know about the extinction risks of climate change. Well, on the left here, you see a slide, you see a graph from a recent meta-analysis that from 2015, which reviewed several hundred studies of the estimates of climate change effects on extinctions. And you see the estimated effect, right? So starting kind of right around now, it's predicted that eventually kind of 3% of species will kind of go extinct because of climate change, kind of rising as temperatures rise non-linearly up to kind of somewhere between kind of 10 and 20%. And these pictures here on the right show you, that these effects are already being kind of felt in U.S. conservation policy. And so the polar bear was the first species to be listed, where climate change was kind of one of the major reasons for it being listed. The North American wolverine in the center was proposed for listing primarily due to threats from climate change. And these two other species here, the Gunnison sage grouse and the yellow cedar, were considered for listing primarily because of threats from climate change, but ultimately kind of not recommended. If we think about the costs of climate-driven changes in extinction risk, we can divide them. A way to conceptualize kind of what these costs are. I kind of like to split them into these four categories, right? So we have, as climate drives extinction risk, we'll have increased spending on conservation. There's a kind of fiscal cost of that additional public spending, right, associated with the fact that public funds need to be raised from distortionary taxes, and that has an adverse fiscal consequence. And then there are these opportunity costs from conservation measures. So this is not the direct spending on conservation, but it's the kind of the cost associated with setting land aside, restricting development, and restricting other types of economic activities in order to conserve these species. These collectively are kind of the public adaptation costs associated with this increased extinction risk. In addition, there's going to be these residual damages, right? And that's going to be lost existence value from extinctions that can't be prevented from these additional conservation measures. So our approach here is we're going to use data on spending under the Endangered Species Act, which, as JL mentioned, this was kind of originally used in the mid-90s by Metrick and Weitzman to kind of look at these revealed public priorities for conservation spending. And we're going to use this to estimate the probability of listing of different species as a function of conservation status and species characteristics. And then we're going to estimate, conditional on listing, how much does each species get spent on it and kind of what determines that. Those two regressions are then going to let us estimate by combining that with estimates from the existing estimates from the ecological literature about how climate change raises extinction risk, is going to let us predict the change in the number of listed species and the change in direct conservation spending due to climate change induced changes in conservation status. The data sources we rely on here. So one key element to be able to predict the listing decision is the conservation status of non-listed species. And so for this, we're relying on a data set from the NGO NatureServe, which has about 60,000 species and subspecies in North America. And it has the conservation status kind of on a ranking from kind of 1 to 5 for most of those species. And then we have this spending data set. So this is spending that's reported to Congress by the Fish and Wildlife Service for about 1,600 listed species. And so this is annual spending on direct conservation at the species and year level. We're combining this with some other cool data sets like a Google Ngram, which measures how frequently that species name appears in the English language corpus. And that kind of gives us a measure of just how prominent, how well-known that species is, as well as other covariates such as the number of Fish and Wildlife Service regions, the range area, the year since listing, and I'll talk about those when I show you the kind of specific regression specifications. So this is showing you some summary data from that NatureServe data set. So this is showing you the conservation status across different taxonomic groups as estimated by NatureServe. And you can see the ranking here goes from secure, where there's kind of no real conservation threat, up to critically imperiled. The numbers at the top are giving you the number of species in the data set. And there's a number of things to notice here that's going to kind of shape how shape my discussion going forward. Firstly, is that the large majority of species in the data set are plants and invertebrates. These are kind of big categories of species. And it's also the case that this purple bar is unknown, right? And so that a large chunk of these invertebrates and these plants have unknown conservation status. And kind of how we treat that going forward is going to have some effect on our results. Oh, sorry. This is the descriptive statistics from the ESA spending data set. And so this is just showing you the median annual spending per species. You can see it varies a lot, right? It varies by an order of magnitude from birds at the high end down to kind of fungi, plants, and invertebrates at the very low end. And just to be clear about what exactly we're talking about in terms of this spending, this is spending on kind of direct conservation measures targeted at a specific species. And so here's a picture of kind of exactly what this might be spent on. So this is one of the co-authors' papers. Sorry, this is one of the paper's co-authors, Ariana, who had an internship kind of last summer where she was working with a rare plant society to basically go out and water these populations of Jessup's milkvetch, which is an endangered species, right? And so it's kind of these measures intended to stabilize and hopefully eventually improve these critically imperiled species. So our listing decision regression is a logistic regression with this binary variable, is this species listed or not? And we model this as a function of the taxonomic status, just the type of species it is the number of n-grams, which is measure of kind of how well known the species is, an ecological measure of taxonomic distinctiveness, and I apologize, but this is missing from the regression, but this is a key factor, and the conservation status, right? And so the errors are kind of block bootstrapped at the family level. And so this is showing you for each taxonomic group and for each conservation status, given kind of the median, like the covariates, what the predicted probability of listing is. And we see a large effect of conservation status on listing probability, right? So it kind of increases as you go to this conservation status 1, which is the most critically imperiled, the probability of listing goes up. But there's also a wide variation across different types of species, right? So we see that mammals are kind of much more likely to be listed than plants or invertebrates, right? And so we see this kind of revealed prioritization given the kind of constraints on conservation spending that we have, that there's just these vertebrate species are kind of much more likely to be listed, conditioned on what we know about conservation status. We do see some effects of n-grams, and we see some effects of this taxonomic distinctiveness measure as well on the probability of listing, and those go in the expected direction. So that's the probability of listing. So we also then model for species that are listed, kind of what are the factors that seem to determine spending. And here we have a kind of a richer set of covariates for this more limited number of species. And so we model this as a function of kind of taxonomic group, status, is it threatened or endangered? Is there some time pattern to this? So the number of years since listing, the size of the range, as well as these internal Fish and Wildlife Service measures of prioritization. And so these are these priority numbers, a measure of whether or not conservation conflicts with economic development, as well as taxonomic distinctiveness. And rather than show you kind of the individual regression coefficients, I'm just highlighting in bold the ones that we find to be kind of robustly statistically significant. We find, pretty strong evidence, which you might expect given the summary graph I just showed you, that invertebrates and plants receive significantly less spending than vertebrates. We also find evidence that spending is somewhat front-loaded, so we find a negative coefficient on the year since listing, suggesting there's some kind of upfront expenses into, once the species is listed. And we find fairly large effects of range area and even conditioned on range area, the Fish and Wildlife Service region. So if for a species that has the same range area, but that happens to kind of coincide with more administrative regions, we find that that species gets more spent on it. So given those findings, and given the species kind of the taxonomic covariates, we can use these regression coefficients to estimate the present cost of 100 years of spending post-listing. So what this is saying is given what we know about these observed patterns of conservation spending, if we were to list a species today, looking out 100 years in the future, in expectation, what is the present cost of those conservation measures that would likely be associated with that species? And here we're looking out 100 years and we're applying a gamma discounting. So we're applying this declining discount rate. So this is again kind of going back to Marty Weitzman. So that we're applying a discount rate that kind of gradually declines from about 4% to 1% at the end of that 100-year time period. And so this is, you can see again, this is kind of summary statistic of like the expected cost of listing in terms of these direct conservation spending. And you can see it varies kind of by an order of magnitude between birds at the highest end, but mammals pretty close as well at about 100 million, down to plants at about 5 million. Oh, sorry, these are in $1 million. The next step of this approach then is to ask, okay, well, we know kind of what seems to determine the probability of listing and the spending conditional on listing, but what then is kind of what is the expected effect of climate change here? And for this, we're relying on this meta-analysis by Urban in 2015, who estimate it was a meta-analysis of previous studies that had looked at the effect of climate change impacts on extinction risk. We're using a subset. We reanalyze that data. We're using a subset of 191 estimates from 32 studies that are just focused on North America. And so we find what I'm plotting here, this expected effect of warming on extinctions. And we find no evidence of, we test for nonlinearity. We test for heterogeneity between different taxonomic groups. We don't find any evidence for that. So we're just going to use this kind of, this linear relationship kind of that, that relates warming to expected extinction risk. And for this, we're using a kind of threshold of a 90% loss in range. So we're saying a 90% loss in range kind of would be equivalent to becoming critically imperiled, and therefore potentially a candidate to be listed. So we can then combine all these pieces together to predict the changes in listing and spending with warming. And we're going to sample from a number of, like, obviously this is a kind of long causal chain I've established here, and we're going to sample from a kind of large number of uncertainties that kind of mediate this relationship. So firstly, we don't know which of these species are at risk of extinction, right? These are kind of an in expectation measure. So we're going to randomly sample repeatedly from the set of species in the NatureServe data set. We're then going to predict the probability of listing given those species-specific covariates, kind of plugging them into our listing model, and then predict the spending conditional on listing using this 100-year expected value. And we're going to sample uncertainty in the temperature effect on extinction risk, the exactly which species are affected by climate change, the probability of listing regression, and the spending conditional on listing regression. So there's multiple sources of uncertainty that are going to be reflected in the error bands, in the error bars that I'm going to show you. A question we have to ask ourselves here is, what about this large number of species with an unknown status? And so one way of thinking about the fact that there are these large number of species that we don't know what their current conservation status is that kind of reflects a revealed prioritization in terms of where we've put the effort to understand kind of current like levels of risk. We take both approaches. I think our preferred approach would be to exclude these unknown species simply on the basis that if climate change is kind of affecting those populations, given what we know now, it's not clear that we would know enough about that to kind of put them on the endangered species list. But I'm going to show you both sets of results. So this is showing you the increases in number of listed species and number of critically imperiled species with increase in temperature above pre-industrial. So this is excluding those unknown species. What you see is kind of a gradual increase up to, by 5 degrees, about 600 species we would expect to be listed. A large fraction of those are plants, just because there's a lot of plants in the data set. But what's really important is there's a large number of additional species are critically imperiled but not listed. And this reflects the fact that we see this kind of filtering stage at the listing decision. If we then look for these listed species, what's the expected increase in spending? We see a kind of linear increase up to about $20 billion if we include the unknown species. If we exclude the unknown species, and about $25 billion if we include the unknown species. So a lot more species get listed if you include the unknowns, but they're mostly invertebrates and plants that don't get much spent on them. So coming back to this categorization of the cost of climate-driven extinction risk, we can say, well, what about all these other pieces of these costs, right? So I've just shown you kind of one estimate of how to, this one smaller category here. So what about these others? Well, we can estimate the fiscal cost of raising public funds. Might add, there's an estimate from Lint Barrage, suggests that we should add somewhere between 6 and 53%, depending on how those funds are raised, as kind of the effects of that distortionary taxation. These other two are potentially enormous, right? These are really potentially very large. The opportunity cost of conservation measures and the lost existence values of these residual damages, but we're not able to bound them here, other than to say there's these large unknowns that are very difficult to put values on. And I think I'm out of time, but I will just leave the findings up here, and I'm happy to take questions.
Thanks so much, Fran. So I'll invite all of our audience participants to type their questions in the Q&A box. Fran, there was one question that's already been entered, which asks sort of how has the Trump administration changes in approach to the Endangered Species Act changed your prediction?
Yeah, so my understanding is kind of none of those changes have been finalized, and I think a lot of them are proposed. I think periodically there's these kind of like pushes on the Endangered Species Act. I think, to the extent we're pointing at this as evidence of, some like revealed public priorities in spending, I would say that, if it does change substantially, that would change our findings. But given the longevity of the ESA kind of today, it's been around for a really long time. And really, the principal measures have not kind of changed substantially over that time. So I think I would probably point to that as kind of evidence that these are fairly stable. But certainly to the extent this is, and I would also say, I think a lot of the controversial pieces of the ESA are not like these direct spending measures that we're looking at. Is much more these like no-take provisions and these critical habitat preservations. It's these the costs associated with these restrictions on development, and we're not able, that in the paper we discussed this literature that kind of has tried to estimate those costs. They tend to be heterogeneous. It tends to be very kind of site and species specific, and so I would say I think it would affect those costs, but I don't think it would have a huge effect on these kind of direct appropriations.
Thank you. So the next question, there are two questions here. I'll give them to you both. So your projection seems to assume that the more species listed, the more will be spent. Are the agencies in charge of species conservation not operating under some sort of budget constraint?
Yeah, that's a good question. That is correct. I mean, that is kind of mechanically how our calculation works. I would say that I think you see there is clearly a budget constraint, right? And that you definitely see that budget constraint bind in the fact that there's a lot of species that are imperiled that do not get listed, right? And, there's nothing in the legal statute that kind of explains why that is, right? But if you look at, there are these, you can have a kind of, I'm forgetting what this decision is called, but there's a decision you can make where it's like, yes, this probably should be listed, but we can't do it, right? Like it's not a high enough priority. And so you see this, budget constraint definitely bind at the listing stage. Is it a zero sum? Is it a zero sum on the spending? Yes, our assumption is that basically the budget of the agency would grow with the number of listed species. I mean, we've seen that kind of happen historically. But, and so we're assuming that would be the case in the future.
Okay. Two more quick questions. Second question, how do you explain the rather linear shape of your spending simulation with respect to temperature?
Yeah, so that comes directly from our estimated effect of warming on extinction risk, which comes from this analysis of which we estimate a linear function. That's different from Urban, who's looking at so we pull out just the North American kind of estimates from his data set. And so he estimates the kind of quadratic. We test for a quadratic, we just don't find evidence for it. And so that's why we just use this linear, kind of the simpler linear response. But everything else is just kind of directly proportional to that. And so that's why there's no non-linearities in those listing and spending.
And then last question, the participant notes that we face similar plant extinction risks here too. What would you say are the best ways to increase awareness on plant conservation spending and increase spending on critically imperiled crops and plants?
Oh yeah, I'm not sure I'm the best person I'm sure there's better people to ask about that, including kind of, my co-author Ariana here. But I think what we point out is that they seem to, not be prioritized right now. I mean, you can see that in the data, you can see that in what the spending, and you see that you also, and so I think, if people, if there was more of a constituency, if they had a more, kind of active kind of, constituency of support around them, maybe that would kind of change things. But this is just pure speculation.
Right, and then I gotta amend my my declaration that was the last one. So Nick asked if further research were able to estimate the regulatory cost to the private sector and the land value impact of the ESA, would those be appropriate to add to the welfare estimates here?
Yeah, that's a good question. It certainly would be a cost of exactly kind of how they fit into the kind of total costs here. I think I would say yes. We would short answer is yes, we would definitely love, but to be able to incorporate those kind of shadow costs, those the cost of those constraints into this estimate. And I think what's important here is a lot of economists, I think, have pointed to the inefficiencies involved in how, say, critical habitat or no-take provisions are implemented. I think what's important to think about adaptation is that the climate change is going to play out in this context of inefficient kind of public laws and spending. And, if we think climate change is going to exacerbate those inefficiencies, that is something to be aware of because, likely those inefficiencies are not going away because they haven't gone away, for the last 50 years. And so, or at least to kind of be aware of how those things might kind of integrate. In the paper, we do try and take a stab at the residual damages, but it's very rough. And if we look at some of the willingness to pay estimates from the contingent valuation literature, but that's pretty much it.
All right. Fran, thank you so much for that.
Oh, sorry. I have one more slide. I totally forgot. So this is just a pitch for a paper coming out soon in Nature Sustainability on a kind of very related topic about how do you incorporate these ecological damages into kind of fundamentally into the social cost of carbon and into these integrated assessment models. So if you're interested in this topic, kind of stay tuned for that one.
All right, thank you. All right, so it's my pleasure to introduce our second presenter, Roger von Haefen. He's a professor at North Carolina State University. I've known Roger for 15, maybe 20 years, and from our recreational demand days. Roger, thank you so much. He's going to talk about the effects of weather on recreational fishing demand and adaptation implications for a changing climate. Roger, the floor is yours.
All right, thank you very much. It's a pleasure to be here. I'm delighted to be a part of this conference. I wish it was possible for me to actually be in Los Angeles, but we will make do as best we can. This research is joint with Steve Dundas, who is an assistant professor at Oregon State University. And really the motivation of this research is, if you look at the outdoor recreation economy, it's a sizable part of the overall U.S. economy. The Bureau of Economic Analysis estimates that it's about 2.2% of U.S. gross domestic product, and a segment of that overall outdoor recreation economy, marine recreational fishing, is also quite important too. About $25 billion in spending and 72 million user days back in 2012. It should be clear that climate change is likely to impact these activities going forward, as the enjoyability of being outdoors is somewhat affected. The existing literature on how climate change is likely to impact outdoor recreation is quite thin. And I put up here a quote from Doug Shaw and John Loomis, which suggests that most of the literature on the damages of climate change is focused primarily on use-related or market-related impacts, and not so much on non-market-related impacts. And I think that motivates both Fran's paper and the current paper. So what we're going to do in this paper is we're going to estimate the demand for shoreline recreational fishing, a particular type of outdoor recreation, with panel data. And unlike the previous literature, we're going to use temperature and precipitation bins to account for nonlinear weather effects. The fact that as it gets warmer, you might expect the effects of moving from a day where the high temperature is 75 to a day where it's 80 is different than the effects of moving from, say, 90 degrees high temperature to 95 degrees high temperature. We want to evaluate the welfare implications of this predicted climate change with 132 global circulation models. And then we're going to investigate heterogeneous seasonal and regional impacts across different regions of the United States. And after we do that, we're going to evaluate a potential adaptation mechanism, which is intraday substitution. The idea being that as it gets really hot, particularly in the middle of the day, people might substitute their outdoor recreation to the shoulder periods of the day, the early morning or the evening, where it's less hot. So this study makes a number of contributions. Oops. It's one of the first studies to investigate how coastal marine recreational fishing responds to climate change. It extends methods that are used broadly in the climate damage literature to the outdoor recreation literature in terms of how you characterize weather and climate, and use panel data to assess the damages of climate change. Our welfare analysis is a little bit different than what's traditionally done in the climate damage literature, where basically people are focusing on losses associated with reduced the number of lost goods. So in our case, the number of lost trips. Well, those inframarginal trips, those trips where people continue to go, but the experience is less enjoyable, so it's a diminished trip, those losses should be counted too. And our methodology actually accounts for that. unlike much of the climate damage literature. And some of our key results are that losses during summer months and in the southeastern and Gulf Coast regions, so where it's already really hot in the summer, those losses are significant. Whereas in the New England region, we predict that there will be gains from climate change as the length of the season increases. And then we also investigate a particular mechanism for adaptation, and that's night fishing. So shifting the timing of your recreation from daytime, where it's extremely hot, to nighttime, where it's less so. Now, I can throw a lot of caveats at this research. We're only considering direct effects of weather on marine recreational fishing. We don't account for ecosystem or indirect effects, so effects on fish stocks. There is some literature that suggests that fish are going to migrate towards the poles with climate change. But really, as far as fine-scale predictions on how climate change will affect fish populations across these different regions, there's not a lot of literature out there. We would love to pursue this literature or this area going forward. So if there's anyone out there that's interested in this topic and has some methods for generating these predictions, we should talk. We don't account for behavioral feedbacks in the sense that if you fish less, you catch less fish, and that means there's more fish abundant in the ocean, which means that your probability of catching fish if you were to take a trip would actually go up. We don't take into account that. We also don't take into account extreme weather events. We had one of these in North Carolina, where I live recently, a hurricane. People out in California can probably tell you about wildfires and how those might affect outdoor recreation. And I would argue that I think you should think of our work as an important first pass, and there's lots of fertile ground for additional collaborative interdisciplinary research going forward. So there is a modest literature out there on outdoor recreation and climate change. It really kickstarted with a book by Rob Mendelsohn and co-authors that used cross-sectional aggregate data to assess how climate change is likely to affect participation in outdoor recreation across 17 different categories. They characterize weather using average temperature across different states in the United States. And they basically find that with climate change, outdoor recreation participation will increase. And so their forecast is that climate change will be good for outdoor recreation participation. There have been some more recent studies and some more micro-level studies. In general, those studies find a similar result, that climate change will be good for outdoor recreation, but that's not universally so. There's a few studies that find that climate change could be bad. And we should recognize that different types of activities, whether you're talking about skiing or fishing or swimming or what have you, they could be differentially affected. So the type of activity, I think, is important when thinking about the impacts of climate change. Now, the data that we're going to bring to this study is collected by NOAA on an annual basis to get at recreational catch throughout the United States. So this is the MRIP, Marine Recreational Information Program data set. It's been collected since the 1980s. There are two big data sets here that we're going to focus on in our analysis. There's an intercept survey where they intercept people at site and they get information on how much fish they catch. And then there's a phone survey, which gets at participation for residents of coastal counties. We have a site registry of all the different recreational sites along the Gulf Coast, along the Atlantic Ocean and Gulf Coast. So we're talking Maine to Louisiana for a 6-year period, 2004 to 2009. We're going to link in PRISM weather data, which is a standard data set that many researchers use to characterize weather over a long time span. And then once we've estimated our models, we are going to use general circulation models to forecast how climate change will impact recreational participation going forward. Here is a picture of the counties throughout the United States that we have recreational data for. So like I said, it goes from Maine to Louisiana. You're talking some very different climates. We'll focus on these 4 different regions: New England, Mid-Atlantic, Southeast, and Gulf Coast, when we talk about the spatial distributional impacts. I'm going to just go through a real quick summary of the modeling approach. This is probably not the right place to go through a detailed discussion. Essentially, what we're going to do is we're going to start off and we're going to estimate a model of site choice. So conditional on taking a trip on a current day, you make a choice of where to go. And that is affected by things like your travel costs or your proximity to these sites, as well as the characteristics of those destinations that you might go to. So we'll estimate people's responsiveness to travel costs and these unobserved site or these observable and unobservable site characteristics in the first stage. Then we have some limitations with the data, so we're going to do a calibration exercise in the second stage to correct for those limitations in the first stage. And then in our third stage, which is really where the weather variables come into play, we're going to model recreational participation throughout these 4 regions of the coastal United States, combine that with these 132 GCMs, and generate welfare and demand predictions. I'm going to focus on the welfare results. I'll try to give you a sense of how the demand results compare, if that's something that you find more compelling. I'm going to just skip the characterization of the model. The key is when we model which sites you go to, travel cost is a key variable, and site characteristics, both observable and unobservable site characteristics that might vary across time and space. We're going to account for that. The data we use, again, is from MRIP. It's over a 6-year period. We have 186,000 trips that are being intercepted in this data set. This is a very large data set. We're going to use rather standard assumptions in the travel cost literature for how to characterize the travel cost of going from where you live to these recreation destinations. And here are some parameter estimates. Travel cost is a strong predictor of where people go. People would rather go to a site that's nearby, ceteris paribus. But of course, if a site that's further away has some really desirable characteristics, they might be willing to absorb those higher costs to get to that more desirable site. Now, in the second stage is where we're going to introduce the weather variables. And here we're going to do this using this binning approach, which is now, I would argue, close to standard practice in the climate econometrics literature. So what we do is we have data which characterizes recreational participation over a 2-month period for all 2-month waves throughout a year. So January, February, March, April, and so forth. And we count up the number of days where the high temperature falls within a 5-degree Fahrenheit bin. And then those counts of the number of days within each of those 5-degree temperature bins are our explanatory variables and how we characterize temperature. So we are allowing for nonlinear effects in the sense that an additional day in that very highest bin might have more of an impact on participation than an additional day, say, in the middle impact. And we're going to account for a number of additional factors that might explain participation decision through year dummies, wave by region dummies, and spatial dummies. The data we use is the MRIP Coastal Household Telephone Survey. We have 1.6 million phone interviews. We have a very large data set, and we're going to link in the PRISM data to characterize temperature and precipitation. Here is a graph of some of our key results. I would focus in here on the highest temperature bin between 95 and 100 degrees Fahrenheit. And what you see is that when it gets really hot, participation declines, and it declines significantly. So people can adapt. The results seem to suggest people can adapt when the temperatures vary between, 50 degrees and 90 degrees Fahrenheit. But when it gets really hot, then people have a hard time adapting, and they tend to avoid taking trips as a result. We don't really find much of an effect in terms of precipitation. This is consistent with the existing climate econometrics literature for other types of impacts. Most of the impacts here are in terms of temperature. And then we're going to use these econometric estimates in combination with these forecasts of how climate change is likely to be affected over the next 30 to 80 years. We're going to consider 132 different general circulation models. So we'll consider a lot of different models, and I'll give you some summary statistics there of what we find. And here, you should be able to see that when we look at representative concentration pathways, 8.5. So this is the predictions that, God help us, are never realized. If we have climate change of that degree, what our model is predicting is a fairly substantial reduction in recreational participation, about a 15% reduction in participation going forward. Of course, if the climate change is less, the effects are less too. But you can see that in general, the results are statistically significant. The gray area is the 95% confidence interval. If we look at the distributional effects across regions, the effects are concentrated in the Gulf region where it's already hot, and then the Southeast region where I live, where it's already pretty hot for most of the year. In New England, in the Mid-Atlantic regions, we don't find much of an effect. In fact, we find modest evidence that recreational participation will increase in the New England region. If we look at how participation changes across different times of the year, what we find is when it's really hot in the extreme summer months, recreational participation declines a lot, but in the shoulder season and even in the off season, recreational participation might actually increase. If you prefer quantitative numbers, we find annual damages on the order of about $311 million for coastal recreational fishing with representative concentration pathway 8.5. Now I want to talk a little bit about adaptation and how people respond to this. So people can respond to climate change by shifting the location of where they recreate, as well as when they recreate. So this temporal, and what we're going to focus on is intraday substitution. So shifting your recreation at night are likely mechanisms through which people might respond to climate change. And we don't find much evidence that people change the timing of their recreation. So if last month was really hot, it's not like you're going to respond by doing more recreation this month to avoid that extreme heat. We don't find much evidence of that. Our results are pretty robust to that kind of behavioral response. But if in terms of night fishing, in terms of the probability that a person's going to shift their recreation at night, we do find significant evidence that recreational participation will increase at night when it gets really hot during the day. And so I think that's an important type of adaptation that we need to think about going forward when thinking about how people are going to respond to climate change. We have some conclusions here, which summarizes what I just told you. I can throw up a bunch of extensions to the kind of research that we want to do and that we're pursuing. And one of the key areas is more of an interdisciplinary approach that accounts for changes in fish stocks with climate change that we'd like to pursue. And with that, I will stop and hand it back to JR.
Thank you so much, Roger. So again, those of you in the virtual Zoom room, or in this case, On24 room, please share your questions. So let's see, one question, well, there are two questions so far, Roger. The first question, have you considered wind speed as another variable affected by climate change in addition to temperature and precipitation that might affect the fishing experience? And then let me give you the second question, if you can just track these. Did you consider substitution with respect to shoreline fishing? I'm presuming as opposed to either not fishing or boat fishing.
Yeah. So it turns out I'll answer the second question first. The MREP dataset has data on boating as well, in addition to shoreline fishing. And we started with the shoreline dataset. And I think one of the extensions that we would like to pursue going forward is to run models with the boating data set. And in that context, I think wind is certainly very relevant and an explanatory variable that we would want to take into account. When we started this project, Steve Dundas, this research was part of his dissertation. We did explore variables like wind speed and the presence of hurricanes. And we didn't get a lot of traction with those variables initially, so we shifted to focusing on temperature and precipitation. But like I said, I think if we expand the analysis to look at boating related activities, I would definitely want to include wind as an explanatory variable. Yeah, the climate and the hurricane impacts, I would like to revisit that again going forward. I think that's a type of impact that's very real, and given the lengthy hurricane season that we're going through right now in the Carolinas, I would expect there to be, just intuitively, I would expect there to be some kind of impact, but that's an empirical question that we need to explore.
All right, thank you, Roger. And both Fran and Roger, I'd encourage you to take a look at the Q&A list and personally respond to any of those questions more completely than you might have thus far, or I might have presented the question. All right, so we've touched on biodiversity impacts and lost recreational angling impacts. We're going to shift now towards agriculture. And our last two papers are going to focus on agricultural dynamics and climate change. Our next presenter is Gil DePaula, Assistant Professor of Economics at Iowa State University, who's going to share a presentation with us on climate adaptation and innovation, evidence from the double cropping boom in Brazil. Gil, the floor is yours.
Thank you very much, Jay. Hello, everybody. My name is Gil DePaula, Assistant Professor at Iowa State and affiliate of the Center for Agriculture and Rural Development, ISU. So I'm going to be talking today about adaptation and innovation. I'm going to study this double cropping boom in Brazil. This is joint work with Ari Fortes. So Ari is an economist at the Brazilian Agricultural Research Corporation, Embrapa. And we would love to hear, I would like to thank UCLA for putting this great event, and we would love to hear any comments you might have. Thank you. So what is the motivation for this research? So what we're really trying to get at here is we're trying to measure long-run economic adjustments. The specific research question is, what is the magnitude, the speed, and constraints of adaptation for environmental change? We're very much thinking about climate change, and we are trying to we understand measuring adaptation is extremely difficult. It's not easy to measure these climate effects and how farmers, for example, respond. Measuring this long-run adaptation, in other words, adaptation that might take years, might take experimentation and innovation, it's even harder. So how we go about this? So to summarize the research design, what we're doing is we're using a historical event. This is very much in line with the work of Hornbeck and Keskin. The idea here is that you have a historical event that affects the environment. And then you see over the years how, in this case, farmers are adjusting that. So what is the historical event here? We are looking at the emergence of soybean rust in Brazil. So that's the most severe disease in soybeans that there is, and it starts in Brazil around 2001. And what happens with the emergence of such a disease is that you have variation in the riskiness of production in agriculture, in this case, production of soybeans. So you have this big disease that shows up in Brazil, and then what happens is that shifts the riskiness of agriculture production. What is the adaptation that we're looking at? We're looking at change in production system, specifically the adoption of these advanced double cropping systems that use some different varieties of soybeans and corns. The double cropping system that we're looking here is first crop soybeans, second crop corn. And how we go about that? So what we do is we use some weather variables. We create a weather data set that captures the probability of a severe outbreak. So we go back to the agronomy literature. We look at how these diseases can become severe outcomes, and we measure that using weather. So then what we do is we compare this adaptation in land with high and low suitability for double cropping, in regions with high severity, in regions with low severity. So what we're really doing here is a triple difference model to capture over time, over the years, how farmers adjusted to this change in riskiness. So let me just summarize the key results. We have 3 key findings. So number one, we see this rapid adoption of double cropping. It takes years. But the idea is that double cropping, or the adaptation here to climate, is a risk management strategy. You have a shifting risk, and farmers adopt this multiple crop system to reduce the risk of producing soybeans and add some revenue from a second crop. So that's first key finding. The second key finding is we find heterogeneous adaptation. So, and we're very much looking to study the limits and the differences in adaptations across Brazil. So we find that particularly in land that is suitable for this multiple cropping system, we find that farmers recover most of their revenue that they had lost. However, it takes about 10 years. So in the first few years, you have a loss, and then you're going to show how they start recovering from that loss. And then finally, we study, once we go through this adaptation process that takes years, how does that change the sensitivity of corn production, corn yields? And what we find is that corn yield becomes more sensitive to changes in precipitation, especially because a lot of the corn production moved to the second crop, which needs rain at the end of the season. But however, the corn yields become less sensitive to the temperature. So once we go through this large adaptation process, we have a different vulnerability of agriculture to climate. So let me first give you a little bit of background. So the idea here is that I have 2 key factors, 2 important factors about this soybean rust emergency that I want to emphasize. First of all, the emergence of soybean is a permanent change in the environment. So it permanently changed the riskiness of producing soybeans. So up to today, there's not really a new variety that completely avoids the disease, or you can't keep applying pesticides because the fungi that cause the disease strengthens with pesticide application. So what I'm showing here is I'm showing a diffusion curve of soybean rust events. So this is measured by an organization called Consórcio Antiferrugem in Brazil. So they track every season over time. The planting season starts around September and October. They track how these events of soybean rust starts through the season. So you see here that the first outbreak in 2005, 2006, you have this rapid diffusion of the soybean rust events, right? You have large and rapid diffusion. And over time, I show you here the 2012 and 2013 outbreak and the 2019, 2020 outbreak. The seasons in Brazil for soybeans, they cross the year. They start in October and go to May. But if you look at what happens is that this diffusion curve is flattened, right? And this is reflecting several of the adaptations that the farmers have been working to this disease. So to give an example, a short-run adaptation would be applications of pesticides. So you can keep applying several instances of pesticides, but that becomes very expensive. The second key point that I want to emphasize regarding the emergency is that we're reasonably comfortable that the emergence of soybean rust in Brazil is an exogenous change in the environment. So that's important, right? Because it's very hard for us to model environmental change, exogenous environmental change. So what happens here is that the soybean rust originally comes from Asia. You have an American soybean rust, but that's not as severe. The really severe disease comes from Asia, and it's spread over wind. So in Brazil, the first observation of this disease was in 2001, 2002 season. That's actually in South America, and then starts spreading. And at the beginning, the farmers didn't really realize it was the rust. So they were confused. There are reports that they were thinking that or other disease. So what we're doing here is we're exploiting this emergency as an exogenous shock in the environment. So then the question is how double cropping, what double cropping has to do with that? How does that work as an adaptation, right? So what I show you now, I hope you can see there's a green block over the diffusion curve. This is just a standard soybeans growing season. So you plant around mid-September, like right now they're starting to plant, and they're going to harvest in May. That's the regular soybean season. So what happens when you have this disease is now you have a race. You have a race between growing the crop, so growing soybeans, and the growth of the fungi, right? So there is now an incentive for you to speed up the production of the soybean crop, right? To reduce your risk of a very bad outbreak of the disease, right? So that's where you start experimenting with different production systems that accelerate the production of soybeans. So then I show here, I add the yellow box. Now I'm showing the multiple crop system. So the green box is the soybeans, and the yellow box is the corn, right? So now you speed up the production of soybeans. And the idea here is you will speed up this production of soybeans using new varieties. So one of the interesting technology innovations that we're looking in this study is this early maturing varieties of short cycle. So you start, instead of going to the full cycle of producing, depending on the region, you can reduce the number of days. And once you use those early maturing varieties, then you can add a second crop, which is the corn. Now, there is a trade-off. There is a yield penalty. So when we speed up the production of the first crop, you have yield loss in soybeans, but you add the revenue of the second crop. However, the corn is not affected by the disease. So that's the adaptation. So you have this multiple crop system that reduces the risk for the first crop, and you get additional revenue. So in order for us to capture and to measure this adaptation effect to this change in production risk, we combine two data sets. The first data set is kind of a standard data set. This is a panel data set at the county level. It's very similar to the types of data set that we use in the US for climate change analysis with panel data set. The interesting thing, and this is produced by the Brazilian Institute of Geography and Statistics, excuse me. But the interesting thing is that this data set shows every year how much was produced for corn in the first season and in the second season. So harvest, quantity, yields for first season and second season. So then we can track the adoption of the multiple crop system. And then what we do is we combine this agricultural data with a novel data set on weather data. And a lot of this data set comes from Embrapa. And what we do is we create three variables. So we have a variable to measure severity of soybeans based on weather data. And what is that? That's the amount of rain in the last 30 days of soybean production. And this is based on agronomic studies, particularly on the studies of Del Ponte, that shows how this moisture increases the severity of the disease. So now we have a measure of severity. Then we have a measure of the growing season length that's based on degree days, and that helps us, that gives an idea of the suitability for these early maturing varieties. And then we have precipitation in first, second season. It turns out that this is very important, especially the precipitation in the second season, because the precipitation in the second season gives you an idea of suitability for the corn that comes after the soybeans. That corn that comes late in the season needs a lot of that rain. If you don't have that rain, that becomes a very risky production system. And we complement those two data sets, the agriculture and the weather, with several other data sets for control variables like potential yields. So I'm just going to summarize the empirical framework. I'm just going to give you the main idea. It's a triple difference model. So what is the idea? I have a treatment experiment and I have a control experiment. So what is the treatment experiment? What I'm doing is that I'm measuring I'm comparing farms with high suitability for double cropping and low suitability of double cropping in a region with high severity, before and after the emergence of the soybean rust. So that's my treatment experiment. Right? So what's the main problem with this empirical analysis? The main problem is that it could be that this rapid expansion of this new production system would happen anyway, right? So regardless of this new severe disease that show up, we should see this expansion. So that's the idea of the triple difference, is that I add a control experiment. So my control experiment is now I'm looking at farms with high suitability and low suitability for double cropping in land with low severity. And I use this control experiment to control for this trends in the adoption of the double cropping system. So in addition to that, we use a series of controls. We have state year fixed effects, and we use potential yield and other market access variables for control. The dependent variable here is the difference before and after the soybean rust. So I do that year by year. So I have a reference year before the soybean rust, and I compare, because the interesting part of this analysis is to see the evolution of the adoption and the adaptation. So let me show you a summary of some of our key results. So here I'm showing you the first outcome, and the first outcome, I'm measuring adoption, right? So I'm measuring adaptation. So what is the measure of adaptation here? It's a measure of the share of the municipality with double cropping system. So it's a measure of acreage. It's a percentage of acreage here. And I'm doing this treatment versus control. So I'm measuring, what I'm showing here is the adoption of double cropping in locations with high severity and high suitability. And what you see is that it takes some time. It's kind of flat at the beginning, and then it starts picking up, and you see this rapid adoption. 10% is a large fraction of adoption, and then it kind of starts to flatten a little bit. So you have this period of rapid adaptation. I mean, it's relatively rapid. It takes about 10 years, but very differentiated, because this is a relative measure of adoption. Then what we do is we look at revenue as a second outcome, right? So it's the same framework, the same idea. I'm doing this comparison with, now I'm looking at high severity with short growing season, because the short growing season captures the suitability of the early maturing varieties. So the suitability to the innovation, right? So what I'm looking here is the percentage change in revenue in locations with high severity and high suitability for the innovation. And what you have is that initially you have this large drop in revenue, right? That's expected with the disease, and then over time it starts recovering. It takes some time, but about 10 years, a little less than 10 years, then you have a flat revenue. So in these locations, you have this almost complete recovery in revenue. Now, there is a cost effect that I'm not capturing here. So I do not have the cost, for example, pesticides. So that's a limitation of this analysis. So this is just a recovery in revenue, which doesn't mean that we completely mitigate the impact of this environmental change. And finally, let me just go through one more result, which once we go through this analysis of adaptation, now we have a new system. About 75% of corn in Brazil today is produced in the second crop. This is a major shift, right? So then we measure, so what is the weather and the precipitation effect after adaptation? So this is just a standard weather panel fixed effects models with that weather and temperature. We do this before the rust and after the rust. And before the rust, we see that increasing temperature reduces by about 4% the yield of corn. After the rust, we see that the increase in the yield in corn is a lot less sensitive to temperature. Specifically in the second crop corn, which is most of it in Brazil, is almost not statistically significant. However, if you look at precipitation, let's look at precipitation in the second season. What happens is that the sensitivity to precipitation almost double. If you look at corn in the second season, the yield is a lot more sensitive to precipitation. And so the result here is that we have this adaptation that takes some time. It didn't have immediately, but once that adaptation goes through, now we have a different vulnerability to weather effects. And I think I'm running out of time. So thank you very much, JR, and thank you I'd love to hear your comments.
Thank you very much, Gil. I'll read one of the questions. So it was, quote, I'm interested in why you chose the soybean rust disease to focus on in your research design. Would you say that this approach will mirror adaptation to global temperature rise and climate change in the future?
And I would say no, it's not a close approximation of a change in temperature. So, and why we chose the rust. It's very hard where we're looking to adaptation that takes more than a year, right? So the immediate adaptation would be, you have a disease, you apply pesticides. So we look at this innovation. It's very hard to find an exogenous change in climate. It's just, we know the problems with cross sections. We know some of the challenges with measuring weather effects. So the answer to your question would be no. We cannot immediately translate that to a change in global temperatures. But what happens is we chose the rust because we believe that's a credible exogenous change in the environment in agriculture. And that shows how some farmers can adapt, but not quickly, but they can adapt, and other farmers does not. So it shows this differentiated effect.
All right, thank you, Gil, very much for that presentation. We'll now move on to our last but not least presenter, Kelvin Malunga, who's a graduate student at Colorado State University. His talk title is Once Bitten, Twice Shy, Direct and Indirect Effects of Previous Weather Shocks on Input Use in Agriculture. Kelvin, the floor is yours.
Thank you very much. So I'll go through this presentation. I'll basically be focusing on looking at the effect of weather shocks on input use. This is a case study that's done specifically in Zambia. I'm working on this with partly with my advisor, Dale Manning. I think Frances might know him, maybe not. So just as a brief introduction, Sub-Saharan Africa is actually predicted to have one of the worst catastrophes in terms of climate change, and is going to be impacted negatively. And climate change is going to reduce yields by about 2 to 27%. And adoption of improved technologies such as fertilizer and improved seed, unfortunately, is also very low compared to other regions of the world. And in the case of Zambia, we have about 90% of the staple crop being produced by smallholder farmers who depend directly on rain-fed agriculture. And so without adaptation, what it means that these shocks are going to be a threat to poverty alleviation measures or efforts. And so in this study, what we attempt to do is to estimate how households adjust input use as a response to weather shocks. And we explore some of the impact mechanisms that explain these responses. And so just a bit of the introduction, because one of the main things that we focus as in explaining the observed responses is actually risk aversion. In economics, the standard economic theory suggests that risk attitudes are actually stable over time. But recently, there's been a lot of literature that shows that actually these attitudes towards risk do change as a result of personal experiences such as financial crisis, trauma from conflict or violence, earthquakes, hurricanes, and all those natural disasters. And risk attitudes, and in the case of weather shocks, they do not only therefore affect the risk attitudes, they also affect the income, and together income and the change in risk attitudes can actually affect the adoption or use of improved technologies. There's actually literature that shows that smallholder farmers being risk averse is responsible for non-adoption of some of these improved technologies. And so it is not well known how shocks actually affect the use of inputs that have different attributes in terms of return and risk. And so part of our study is to therefore combine these two impact pathways that is rarely done in literature to estimate the impact of shocks directly through risk aversion and through income effects. So I think this kind of brings us to our objectives and basically what the contribution is and what we do in this paper. So we answer 3 objectives basically. I look at the effect of previous weather shocks on fertilizer and improved seed use. I also look at how the attributes of fertilizer and improved seed in terms of their return and the effect on risk. or production risk, so to say. And I determine the effect of weather shocks on risk attitudes. And this contributes to the literature because I address issues related to technology adoption by causally estimating the effect of shocks on input use. I also account for both the direct and the indirect effect. And I show through different explorations that these observed input use decisions after a weather shock are actually driven by risk aversion. So just briefly, I'll not talk very much about this, but I'm not sure if you can see that, but there are two contradicting threads of literature. One is literature that argues that individuals or households become risk-seeking after a shock. And there's theory that has been developed on this, and there's also empirical literature that shows that individuals become risk-seeking after experiencing a negative shock. And it's explained that this is done to cover the losses you incurred. And there's also a second thread of literature that shows that actually individuals become risk-averse after a shock or a negative or a loss. And there's also a theory which has been developed for this, which is basically talks about history-dependent risk attitudes. And there's a lot of also empirical work that has been done to show that after experiencing a shock such as a financial crisis, health shock, or even natural disasters, individuals do become risk-averse. And so it is not clear actually in literature, it's inconclusive as to what happens after a shock. And so part of our contribution is to estimate this in a developing country context on smallholder farmers. So just a bit of the context and what we call the impact pathways. So we have two main impact pathways. One is a shock in period T-1 could affect input use in period T directly, and we call this the risk aversion channel. But a shock in period T-1, such as a drought, could also affect income, which imposes some liquidity constraints on input use in period T. Now, our argument is actually that this income here is not endogenous to the input use decisions in period T, and this depends on the timeline of agricultural decisions in Zambia. Basically, you have the rainfall season, or the rain season from about November to March, and then you have the marketing season, and then the decision to use inputs is made, and then you have another rainfall season, which is concurrent with the growing season. And so input use decisions are made around October, and therefore income, which is earned in from the previous harvests, is not correlated with the decision to use, at least it's not endogenous on the decision to use inputs in period T. And we empirically test this, we find that droughts in period T do not affect this income. However, previous shocks do affect this income. And so we argue that this income here actually can be modeled without fears of indigeneity. But in terms of the data we use, so I use a national representative data, which is from 8,000 households collected in 2012 and 2015 by an institute called Indirect Agricultural Policy Research Institute with support from Michigan State University. And I also combine this data with rainfall data, which is TAMSAT. And I define rainfall shock as simply an anomaly. And if it's less than minus 0.5, this means there was a drought. So the formula here is simply the long run rainfall average, which is for 34 years. Our rainfall data is for 34 years, minus what the rainfall was for that year divided by the long run standard deviation. And this is defined as an anomaly. And if it's less than minus 0.5, we feel there's a drought. And so we only focus on droughts. Then in terms of the technology bundles and weather variables, as we can see here, the blue part represents droughts. The more is this yellow or orange, The yellow part represents more of floods. And so we can see most of it is actually, and this is the map of Zambia, by the way. I just superimpose the weather, the rainfall anomalies on the map of Zambia. And we can see that most of it has to do with droughts more than actually having a wet anomaly. And here it's just a summary of the key variables. And the most ones we're interested in is fertilizer use and improved seed use, which we can see that is varies from year to year. And this, we argue that part of this depends on the rainfall patterns experienced in the previous season. In terms of the model, basically I estimate X as Xj, where J is equal to fertilizer or improved seed. And I estimate the probability of using this input as dependent on previous weather shocks, which is WNT minus 1, and a host of other variables here. I'm interested in just the effect of other weather shocks, or previous weather shocks. And therefore, this represents the direct effect. And then I also estimate the effect of these shocks on income, which was earned in the previous season. And indirect effect is calculated as simply a product of this multiplied by that. And the total effect is simply summation of the indirect and the direct effect. The standard errors for estimating the indirect and the total effects are bootstrapped. And I use the exogenate of shocks, weather shocks, and also the fixed effects for identification. And because weather shocks are objectively measured here, and we assume that once we condition on the household fixed effects, weather shocks are more like a random draw. Then I explore the impact mechanisms that explain this, and I basically use the the expected utility theorem here, and so assume that we can approximate the utility of output from 3 moments, which is the expected output, the variance of output, and the skewness of output. And therefore, I determine the effect of fertilizer and improved seed use on the expected output, the variance, and the skewness to measure the return, the risk, and downside risk. Skewness basically measures downside risk. And because input use in the previous model might be endogenous, input use and yield might be correlated. And so I instrument for input use with variables that I think are not correlated with yield, but they are correlated with the likelihood of using improved seed or fertilizer. And these are distance to the nearest agro dealer, access to extension services, distance to the nearest government fertilizer depot, and average maize prices in the district. I use those as instruments for fertilizer and improved seed. And I also estimate the effect of shocks on risk attitudes. I'll not go into the details of the model, but basically I use the Arrow-Pratt measure of absolute risk aversion and downside risk aversion to see if shocks actually affect risk attitudes. In terms of the results, the first one is the effect of, we can see that a drought in period T-1 leads to a reduced probability of using fertilizer, and also an increased probability of using fertilizer in the following period. And the indirect effect, which is through income, is very small, just about 7% of the total effect. And this holds whether I control for household characteristics, household level variables, and other variables. And so to try and explain why there are these differences in observed input use resulting from previous weather shocks, I go into exploring why this might be that improved seed, there's a higher likelihood of using fertilizer, lower likelihood of using. Now, these might be complementary inputs. I know we might be thinking about that, but there's about 70% of the households that use only one input because of cash constraints and such things. And when I estimate on using both of them, the results actually are not significant. They cancel out. So I also do some heterogeneous tests to find out if the impacts are different across things like access to credit, gender of the household heads, and also wealth. And on gender, I find no differences. On access to credit, I find that actually those with access to credit, there's no negative effects of previous weather shocks on the likelihood of using fertilizer. But those without access, actually they reduce the likelihood of using fertilizer in the following period. And in terms of the mechanism, I determine first what are the attributes of the two inputs to try and explain the observed results. Why is it one input is more likely to be used, the other one is less likely to be used after a weather shock? So what do I find? I find that improved seed is a low return input, and this has been found a lot in literature, that on its own, improved seed doesn't actually increase yields, but is actually a risk-reducing input, as we can see, with relative to the variance of output and also the skewness, which I call downside risk. Improved seeds reduce downside risk, and they reduce absolute risk as well. And in terms of fertilizer, we find that it's actually a yield-increasing input, but also risk-increasing input. So this means that then, if a household is risk-averse, they're more likely to adopt a low return but risk-reducing input and not adopt a high return and risk-increasing input. So does this mean households that experience weather shocks then become risk-averse? Is this the reason for the observed effect of weather shocks on input use? I do estimate the effect of shocks on risk attitudes, and I use the arrow plot, AP, and downside risk. And here I split the sample into two subsamples, those that experience shocks in period T-1, which is the previous year, or the previous agricultural season, and those that did not experience shocks in period T-1. And what I find, so here, if the arrow plot coefficient is positive, it indicates risk aversion. Same with the downside risk coefficient. If it's positive, it indicates risk aversion. And the higher it is, the more risk averse that household is. And I find that actually the households that experienced a weather shock in the previous season are more, and then after doing the subsample analysis, I compare the coefficients using a word test. And so the difference here is simply the difference in the coefficients for AP and DS. And so I find that households that experience the weather shock in period T-1 are actually more risk averse compared to those that did not experience. This holds qualitatively for downside risk as well, but not significantly, statistically significantly. So then, in conclusion, I conclude that these observed impacts of differences in risk attitudes and inputs characteristics explain the observed results. Then I also do some other analysis to find out if the observed decisions could be explained by expectations. And here I have rainfall data, remember, for 34 years. And I simply do a correlation of a drought in period T-1 with a drought in period T. And I found that there's a negative correlation. This means that if households are rational enough and they have rational expectations, after observing these patterns for so long, then they should actually not become risk averse. They should become more risk seeking, because a drought in period T-1 is negatively correlated with a drought in period T. And this is graphically confirmed here. So in conclusion, I think I'll just leave this hanging. I think I'm running out of time. But
you can. Why don't you go ahead and why don't you hit the high points of your conclusion, Kelvin? And then so far we have one question.
So just in conclusion, what we find that as weather shocks or climate change, weather shocks or extreme events resulting from climate change has an impact on risk attitudes, and it results in farmers becoming more risk averse and hence less likely to adopt high return but risk technologies. And this has actually an impact on poverty. And we find that actually access to credit could help to mitigate some of this risk aversion behavior, and it could allow farmers to use risk inputs. And the other one is probably throughout, I didn't highlight, but income in the previous period was correlated with high likelihood of using both fertilizer and improved seeds. So income enhancing productivity gains could actually offset some of the negative effects of shocks on the use of risk inputs. So that's the end. Thank you.
Thank you very much, Kelvin. So the first question comes from your co-presenter, Roger, and he states, I'm assuming there's no crop insurance markets in your application, correct? In the US, changes in the generosity of crop insurance subsidies has been used to learn about farmers' risk preferences.
Yeah, no, yeah, I mean, Zambia, in the developing country context case, there's absolutely no insurance markets for crops. I mean, the other countries that are trying out weather-based index insurance, but it hasn't just picked up in all the countries. Still very much donor-supported projects for now in a few countries.
Mm-hmm. And then, Kelvin, I'll ask you a question since I think this will be the last one. I have seen in other settings of natural disaster impacts a similar risk preference shift, but they note that its duration is relatively short in period and length, lasting usually no more than 2 to 3 years. And that's even for impacts like tsunami strikes and rebuilding practices. Do you have a sense of what the duration of your response is?
I do not have a sense of the duration of my response, but I would assume it's also short run because, first of all, because I do not have data collected over a long period of time, so I'm not able to estimate shocks. My household data is only for 2 years, so I do not have a very long panel. Then secondly is that there are a few studies that have been done that also show that. One is in Italy. I think they did a study on the effect of shocks on, they found that actually over long term, they are silent, but also there are contradicting studies. There's a study which was published in, I think, Economic Perspectives and Applied and Economic Perspectives, and they showed that actually the effect of the 2011 earthquake, Greater Japan earthquake, actually lasted all the way up to 5 years. Like, actually the magnitude of the effect between the first year and the fifth year was actually almost the same. So it's, yeah, I think it's not conclusive.
Okay, and then one last question came in, which your study is predicting in the future, I think, increased use of specialized planting technologies that it might be fertilizer and water intensive, but I guess the question is, given the changes in the availability of fertilizer and water in the future, do you expect that, how do you anticipate that some of the climate sensitive inputs would change over time?
That's a very good question. There's also quite a thread of literature. I even have some of, I have done some of the regressions, for example, to estimate whether farmers are more likely to intensify use of fertilizer, whether farmers are more likely to use soil management practices. And so, I mean, these inputs can offset the productivity losses. So as climate change becomes a threat, there's a dual channel that some farmers could use them more to offset the losses from, climate change. But also because of this risk aversion channel, it's like it's counteracting each other.
All right, Kelvin, thank you so much for that. That was terrific. So this brings us to the conclusion of our session today. I want to thank our 4 panelists for their hard work and sharing their findings with us this afternoon. I'd also like to thank Peter Rockmore and Christian Zarate, who have provided technical assistance behind the scene. And I want to thank all of you, our participants, for hanging in there with us to the very end. This concludes today's symposium. If you missed a session you'd like to see, we should be sending out links to the recordings for the 17 sessions that we had today shortly out to you. And then I just want to say thank you all. We hope to do this again, if not next year, at least biannually. I hope you all have enjoyed it, and I hope you have a great week. And I would just invite, again, our presenters to look at the Q&A box and answer any questions that I didn't have a chance to present to you. Thank you all. Bye-bye.